center tap delta system is characterized by having one of the three phases of the delta winding center tapped and grounded. This grounded center tap serves as the neutral for the system and allows for the derivation of 120 volts. In the scenario described, where measurements of 240 volts are observed between phases and 120 volts are found between phases and C to ground, with phase B registering approximately 208 volts to ground, this indicates a center tap delta configuration. To obtain 120 volt receptacles from this setup without resorting to a transformer, it is necessary to connect the receptacles to the neutral bus within the main cabinet. It is highly probable that such a neutral bus exists within the main cabinet, a typical feature of industrial electrical installations. This neutral bus is intended to be connected to the neutral conductor of the incoming power supply. Connecting the neutral of a 120 volt receptacle to the equipment grounding conductor is not a recommended practice, as it introduces potential safety hazards. A properly sized neutral conductor must be used to provide a safe return path for the unbalanced current of 120 volt loads. The system in question is indeed a center tap delta system, as opposed to a corner grounded delta system. The key distinction lies in the grounding point. In a center tap delta system, the neutral is derived from the midpoint of one of the delta windings, offering two phases at 120 volts to ground and one phase at 208 volts to ground, commonly referred to as the high leg or stinger leg. A corner grounded delta, on the other hand, has one of the phase corners grounded, providing a different voltage relationship to ground. To install 120 volt receptacles, firstly confirm the presence of the neutral bus within the main cabinet. Visually inspect the cabinet for a dedicated neutral bus bar, usually identified by a white or grey color code and properly labeled. Secondly, verify the voltage between each phase and the neutral bus. Expect to measure approximately 120 volts between phase A and neutral, and between phase C and neutral. Phase B to neutral should measure approximately 208 volts. Thirdly, never use the equipment grounding conductor as a neutral. The equipment grounding system is designed to provide a low impedance path for fault currents to return to the source, facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. It should not carry normal operating current. Fourthly, run a dedicated neutral conductor from the neutral bus in the main cabinet to the 120 volt receptacle outlet. The neutral conductor should be sized appropriately for the anticipated load, as specified by the National Electrical Code (NEC). Fifthly, ensure that the equipment grounding conductor is properly connected to the grounding terminal of the receptacle outlet and is connected back to the main grounding electrode system. The equipment grounding conductor provides a path for fault current in the event of a ground fault. Sixthly, use properly rated and listed electrical components. Receptacles, wiring, and overcurrent protection devices should be rated for the voltage and current requirements of the circuit. Seventhly, all work should be performed by qualified and licensed electricians in accordance with all applicable codes and regulations. Understanding the specific characteristics of a center tap delta system is essential for safe and reliable electrical installations. One must consider the high leg voltage and ensure that it is properly identified and that precautions are taken to prevent accidental connections to 120 volt circuits. The high leg is typically marked with orange-colored tape or paint to clearly identify it. The NEC provides specific requirements for the identification and use of the high leg in Article 110.15, which mandates its identification, and Article 215.8, which requires the high leg to be the B phase when viewed from the front of the switchboard or panel board. When working with any electrical system, safety must be the top priority. Always de-energize circuits before working on them, and use appropriate personal protective equipment (PPE) such as insulated gloves and safety glasses. Double-check voltage readings before commencing work to ensure circuits are de-energized. Understand the overcurrent protection requirements, which is an integral part of any electrical system. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from overloads and short circuits. The size of the overcurrent protection device must be matched to the ampacity of the conductors it protects. The NEC provides detailed guidelines for selecting the appropriate overcurrent protection devices in Article 240. Ground fault circuit interrupters, GFCIs, are critical safety devices that protect personnel from electric shock. GFCIs detect ground faults, which are unintentional electrical paths between a current-carrying conductor and ground, and quickly de-energize the circuit. The NEC requires GFCI protection for receptacles in certain locations such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters of size are designed to protect against fires caused by arcing faults. Arcing faults are dangerous electrical conditions that can occur when insulation breaks down or connections become loose, creating a high-temperature arc that can ignite surrounding materials. The NEC requires FSI protection for branch circuits supplying outlets in dwelling units. Voltage drop is an important consideration in electrical circuit design. Voltage drop is the decrease in voltage along a conductor due to the conductor's impedance and the current flowing through it. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. Conductor ampacity is the maximum current a conductor can carry continuously without exceeding its temperature rating. The ampacity of a conductor depends on its size, insulation type, and installation conditions. The NEC provides ampacity tables in Article 310.13 that lists the ampacities of various conductors under different conditions. Grounding electrode system is a critical component of the electrical system that provides a path for fault current to return to the source. The grounding electrode system typically consists of a ground rod, ground plate, or underground metallic water pipe that is connected to the building's grounding system. The NEC specifies the requirements for grounding electrode systems in Article 250. Bonding is the process of connecting metallic parts of the electrical system together to create a low-impedance path for fault current. Bonding helps to ensure that all metallic parts are at the same potential, reducing the risk of electric shock. The NEC specifies the requirements for bonding in Article 250. Electrical panels, also known as panel boards, are distribution points for electrical circuits. Electrical panels contain circuit breakers or fuses that protect the individual circuits. The NEC specifies the requirements for electrical panels in Article 408. Conduit is a protective enclosure for electrical wiring. Conduit can be made of metal or plastic and is used to protect conductors from physical damage and environmental factors. The NEC specifies the requirements for conduit in Article 340, Article 352, Article 356, and Article 358. Cable is an assembly of two or more conductors enclosed in a jacket. Cable is commonly used for residential and commercial wiring. The NEC specifies the requirements for cable in Article 300 and Article 334. Terminations are the points where conductors are connected to equipment or devices. Proper terminations are essential for ensuring reliable electrical connections. The NEC specifies the requirements for terminations in Article 110.14. Wiring devices are components such as receptacles, switches, and lighting fixtures. Wiring devices are used to connect electrical equipment to the electrical system. The NEC specifies the requirements for wiring devices in Article 404 and Article 406. Lighting is an essential part of any electrical system. Lighting provides illumination for safety, security, and productivity. The NEC specifies the requirements for lighting in Article 410. Motors are electromechanical devices that convert electrical energy into mechanical energy. Motors are used in a wide variety of applications such as pumps, fans, and compressors. The NEC specifies the requirements for motors in Article 430. Transformers are electrical devices that transfer electrical energy from one circuit to another. Transformers are used to step up or step down voltage levels. The NEC specifies the requirements for transformers in Article 450. Generators are electrical devices that convert mechanical energy into electrical energy. Generators are used to provide backup power during power outages. The NEC specifies the requirements for generators in Article 700 and Article 701. Capacitors are electrical devices that store electrical energy. Capacitors are used in a variety of applications, such as power factor correction and motor starting. The NEC specifies the requirements for capacitors in Article 460. Surge protection devices are devices that protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, utility switching, or other electrical disturbances. The NEC recommends the use of surge protection devices in Article 280. Harmonics are distortions of the sinusoidal waveform of alternating current. Harmonics can be caused by nonlinear loads, such as electronic devices and variable frequency drives. Harmonics can cause equipment to overheat and malfunction. The NEC recommends mitigating harmonics in Article 220. Power quality is a measure of the quality of electrical power. Power quality problems can include voltage sags, voltage swells, and harmonics. Power quality problems can cause equipment to malfunction and reduce efficiency. The NEC addresses power quality issues in various articles. Energy efficiency is the use of less energy to perform the same task. Energy efficiency can save money and reduce environmental impact. The NEC promotes energy efficiency through various requirements. Renewable energy sources are sources of energy that are naturally replenished, such as solar, wind, and hydro. The NEC addresses renewable energy sources in Article 690 and Article 694. Safety is the most important consideration in any electrical installation. Always follow safe work practices and use appropriate personal protective equipment. The NEC provides safety requirements throughout the code. Remember that while this information is intended to be helpful, it is not a substitute for professional electrical advice. Consult with a qualified electrician for specific guidance on your electrical projects.